Ah. So yeah, so welcome back. As I was saying that this course is about giving some glimpses of AI and ML for engineering applications. As Industry 4.0 is beginning, has been on its way, but for it to take off is, it depends a lot on data, on our ability to handle data. And as I was telling earlier, that this topic or these areas is linear algebra, and so these tools derive their foundations based on statistics. And is to just go through statistics. So do I won't say a deep dive, but some recollecting statistical notions. And hopefully throughout the course, you should be able to see how that plays a role in the different topics that get covered. So with that, let me I'll essentially do the first three topics, first 3-4 topics. So, and then Professor Manibhushan will do, some topics tomorrow, which will include interval estimation and hypothesis testing. So what I'm going to do is probably something that you have looked at many times. Finally, let's just do it because that becomes the basis. That allows us to make progress, to use it just as a tool or to be able to interpret our results and make advances. So we decided we will just do these first three topics just to jog our memories. So to put it in perspective, we have a process plant or some other source from a particular data set sees is only a sample. So we have this notion of an ensemble and the notion of a sample. So if you see outputs that the process plant could give you, okay, and you'll say, well, the outputs change over time, and even let us say if I am measuring the ambient heating, it does not remain rock steady. So that is the reality that we have to deal with, that the data is, there's an ensemble. So if I had got known everything about that particular sensor, so what very well, but what we get is not if I anyway had the entire ensemble of all possible outcomes, but unfortunately only the samples. And what we know is that the true parameter is given, say it's a true value, it's not really what black value is, or that black line, and that is where the challenge is, that I and the fact is a data analyst, which is what is to be able to use that realization, okay, in order to make an estimate of the true underlying parameter. for the most Bayesian approach, we say the underlying parameter itself is having a probability distribution, and you know, all new methods in AI are using Bayesian approaches over frequentist approaches. And that seems to be the current trend in AI literature. Like shown over here, you have a dependent variable, some augmented variables. For example, you have mass flow rate and temperature. You can multiply them so you get some measure of enthalpy. Or you could use nonlinear transformations of those variables. For example, you know that the square root of the flow rate, and so you can try to bring those first principles. I always have to deal with outliers being present. I have to deal with missing data, okay, and all these different uh, uh, problems that beset our data set. So we have historically been calling them as two different problems. I really mean to say I'm doing some kind of over here, okay. So,
Sir, hello, sir.
yeah.
Your voice is breaking like periodically, like in between.
Oh, is it?
So I don't know.
Okay. Um, you want me to? It's
Yes.
Actually,
Yeah,
when
it's
we
breaking
so
in
try
between. Yeah.
the
okay.
problem can be solved.
Uh, Exit. Then this meeting will get.
Oh no.
I'll
Sorry,
just.
are you recording in the local system or in cloud, sir?
I'm recording in the cloud.
Okay.
Should I
Maybe
No, it's
record?
no, sir. No, sir. Cloud is fine. Maybe you can disable your video and see
Oh,
if it's a bandwidth issue. Then that will solve it.
um, I so first let me go and check my video from here. Let me go back and let me also just open my door so that if it if that is the issue. Okay. Om Prakash, let me know if it continues. The issue continues.
Okay, sir.
Yeah. So as I was saying that we really have two main problems that we deal with. One is regression, where we are trying to find a model of using the inputs and outputs. So you have a sense of inputs and outputs, and the other is classification, where you are trying to categorize the output. Okay, so those are the two main type of problems that you solve. Um, so you know, there are a large number of tools that are available, and all of these tools are based on statistics. So if you want to be able to understand that, okay, I have a model. So let's say we have y is equal to mx plus c, and m and c we have identified using data like we spoke about in the previous class. Then the question is, what is a 95% confidence estimate of m? What is the 95% confidence estimate of c? Okay, and using this, if I make a prediction, what will be my range of the prediction? Okay, that I have a particular point value, but I would like to know what is this interval value of my prediction. And I can, give you covariance of my estimate, so I can tell you what is my confidence in the prediction and so on and so forth. So to be able to fully make be able to fully use that data set that you have to go through tools of statistics. Okay, so as I said over here, that statistics provides the fundamental framework in which we use these tools. Okay, so let me, just go ahead. As a simple example, we all have seen scatter plots and correlation coefficients. We understand that correlation coefficients give us a measure of linear association between two variables, and these are indeed such kind of notions are indeed used whenever we try to use any data kind of solution. So I've given you an example here where you have an atmospheric distillation column. This was from a live refinery, and we wanted to predict a hard to measure variable, which is a quality of the kerosene. And when you go to the plant, if you have to say, okay, what are these predictors that I should use? So I had shown you that table earlier. Then you will see that the predictors can be so many. So these are candidates that you have, but you would like to know, out of these 59 candidates, should I use all 59, or should I do some kind of a variable selection step, and so on. So um, in order to do that, for example, one thing that we did was we use simple correlation coefficient that we spoke to you in the previous slide. Professor Goody also referred to partial correlation coefficients. So you could have, for example, you have two predictor variables that you're using. One predictor variable is pressure drop at the top of the column. The other predictor variable is pressure drop at the bottom of the column. Okay. Now you know that these two might be correlated. That is, these two inputs themselves are correlated. And so when I use these inputs to be able to predict the quality variable, it might make sense not to include both, okay? To include only one. So you can see that the correlation coefficient with pressure drop at top was 0.72, the sign being negative, excuse me. And the pressure drop at the bottom also was not insignificant. This correlation was not insignificant. Okay, but once you take the partial correlation coefficient, then you're saying, okay, tell me what is the correlation coefficient between this pressure drop at the top, okay, with the quality variable by adjusting for this effect. And the moment you do this, you find that pressure drop at the top is a better variable than the pressure drop at the bottom, because you have adjusted for the collinearity between the inputs. So later when you do PCA, PLS, you will see that the principal component analysis has a very elegant way of dealing with such collinearity. Okay, and a partial correlation coefficient also tells you about collinearity between different variables. Um, Other type of variables. So in the previous case, I was trying to give you an example of a steady state kind of a data, but other kind of cases where you use AI ML is, for example, time series data. So I've just taken a random plot of some stock exchange data over here. I've taken some various plots about the PM 2.5 concentration particle pollution and emergency room visits for cardiovascular diseases. And there might be some kind of a correlation between these two. That is, if this particulate matter goes up, then the cases of cardiovascular disease goes up after a month. So the on the x-axis is given a month. So you might be able, you might say, okay, this is the particulate matter at time t. How does it correlate with cardiovascular disease at t plus tau? And you might be able to see that there is a correlation. Okay. So again, these kind of problems or analyses you can do once you use some statistical tools. So the one very popular tool which is used is called LSTM neural network, okay, which tries to look at such recurrent or such time series data. And we will talk about this later in the course. Okay, so there are some simple ways of looking at data. Firstly, you could look at a histogram. Okay, you could look at probability plots to check what is the underlying distribution. So, for example, in Octave, you can use the command hist, or in MATLAB, and you can use the command prop-plot, where you take data and you try to plot it using a probability plot for a uniform distribution, and you see whether it lies on a straight line or not. So this is a probability plot graph. Or if you wanted to look at normal data, you can try to see whether it lies along a graph. So you can make some assessment. Does this really belong to normal distribution, or is this distribution non-normal? Okay, because a lot of your analyses will depend on the underlying distribution. For example, if you want to find out the confidence interval or do a hypothesis test, and if you do not have a good idea of what is the underlying distribution, those tests and those intervals will be invalid. Okay, so it's very important to have some idea of what is the underlying distribution. So let's look at data. So finally, what you get is y of k, as we discussed in the beginning. There might be a true value, which was like that solid black line I was trying to show you, and then you have this noise which overlays on it. Okay, so what you see is an addition of the true value and the overlaid noise. And the whole idea is that from this true value, from this measurement, which is not the true value, you want to be able to estimate what is the true value. So if this was not there, then there was no question. Once I know the measurement, I believe in it perfectly. There's nothing more to do. But the fact is that my measurements, as we saw from those strip charts right in the beginning, is that there is always noise. And what we see is a realization of noise, not the ensemble. And so we don't, so from that realization, we have to be able to make some comment on what that Y star is that we are after. So as another example, you can see that y of k is, so you can ignore the top graph, just come to the bottom graph. The blue line is y star k, the true value. But what you get is not the blue line, what you get is the black line. And the black curve is the measured value. So, and these two are different. So you never have access to the true value. In fact, it is your purpose of doing data analysis to be able to find out what is that true value. Okay. And so if you give me 5 samples and you tell me find out the mean, then I can always find out the sample mean. Okay. But this is not what I'm after. The sample mean, if you give me new 5 values, I'll get a new sample mean. So I'll get 1 by 5 summation of xi. Every time you give me a new set of samples, I'll get a new sample mean. So the sample mean is not what I'm after. What I'm after is the true population mean, the true ensemble mean. Okay. And so we say that the true ensemble mean, for example, if that was y star, then I have some noise that I overlay on it, and what I get is xi, and I don't, or y, and I don't get y star. But what I'm after is not the sample statistic, but I'm after the true population statistic. So that differentiation is extremely important. So this is the noise. If you knew what the true value was, you could always back out what the noise is. But the challenge is that you never know what that noise is. So that is a physicist view of looking at data, that there is an underlying true value, and but what I get is measurement, and it is not the true value. So a statistician's view of data is that this E of k. So if I write down y is equal to y star plus E, that this E of k, while I have a given realization in my specific experiment, the E of k belongs to some probability density. Okay, and for example, what is shown here is a Gaussian kind of a density, and so there is that population or the ensemble, and what I see is a few realizations of that ensemble which showed up in my measurement. Okay, and so if I can So for example, if I say it is normally distributed with mean 0 and variance, let us say sigma square, then I can say, okay, I can try to characterize this density. If I am successful in characterizing this density, because E, though it is an erratic behavior for my realization, it belongs to a stable density. So the long term, or like they say, the large sample behavior is a stable behavior. And so if I can model it in this particular way, then I will still have a chance of finding out or giving you a better estimate of y star. I may not be able to give you, or for example, I was trying to tell you in the previous slide of that underlying population mean. So while I may not be able to give you the point value of this mean, I can always give you some confidence interval. Okay. So the whole idea is how do you characterize that uncertainty that comes because of E. Okay. All right. So there, so essentially there are two topics in statistics. So most of the statistics can be broken down into two topics. One is, so if I remove descriptive statistics, and so you have inferencing. How do you obtain the true y star from corrupted yk? That is one. So everything from confidence interval to hypothesis testing to regression, classification, all comes here. So if you're using a neural network to do classification, you're actually solving a statistical inferencing problem. And you can ask yourself the same problem. So if you use any a good software, for example, and you obtain the weights and the biases, it will not only tell you the weights and the biases, it will tell you the uncertainties in the weights and the biases. It will be able to characterize, if under some assumptions, it will be able to characterize what is the uncertainty in the predictions and so on. Because essentially everything boils down to to these fundamental concepts. The second topic is decision making. Okay, so this is like a control problem, that having obtained y star, what action should I take? So I can take action which will minimize the misclassification rate, or I can take action which will minimize the expected loss, and so on. So this is another whole different ball game. Okay, so optimal decision making or statistical decision making and statistical inferencing. So the first part you can think of as modeling, and second is having obtained the model, what do I do? Okay, and why do I ask this question? What do I do? Because my model, if I call it with a construct M, I know that this M itself is uncertain. So given an uncertain model, and why did M become uncertain? Because if I think of data D, then I know that the data was uncertain. And why was the data uncertain? The data was uncertain because of noise E. So because there is uncertainty of noise, my data becomes uncertain. I get Y and not Y star. And hence I get a model which is uncertain. The parameters have some confidence intervals associated with them. And so with an uncertain model, how do I take decisions? So it is decision under uncertainty, okay, which is statistical decision making. So an example of regression, this is for that the same refinery problem. They use some kind of a neural network to be able to predict what the kerosene quality is, given after having reduced those 59 variables, I think, to around 6 or 7 variables. So they did a lot of correlation, so that's a general problem of variable selection. And once you can do that, then they reduced it from 59 to 7, and from 7 they came up with some kind of a model. Okay, or you could have, for example, a classification example, and you may have heard of some K-nearest neighbor algorithm, which is a very popular way of doing classification. And here you can see, I think what is shown over here is that you have different flow regimes. You have laminar, annular, homogeneous, and so on. And there were 17 different descriptors. Okay, so they used a K-nearest neighbor algorithm, which is part of an AI ML set of tools, which is a very simple algorithm. It just, there is a training set, and from the training set it says, okay, if I take this point, if you can see that, then I say which is my one nearest neighbor. And if you see that your nearest neighbor is, if your nearest neighbor is belongs to the blue category, then we say, okay, this point also, because this nearest neighbor is blue, this is also a blue flow regime. Okay, so you can have 3 nearest neighbors, 31 nearest neighbors, and you can see that the lay of that of the data of the 17 dimensional data set would predict differently. What they have illustrated here is only for 2-dimensional data. Okay, so with that as my half an hour I have taken for giving you some kind of a motivation, I'll now jump into some some basic notions of probability and statistics. So as I said, there are two broad areas that you can approach probability. One is, of course, the frequentist approach, which believes only in the data. Okay, and the other is a Bayesian approach where you have prior knowledge. So, for example, Professor Gudi had referred to using first principles knowledge in my data-driven approach. So, for example, if I know that one particular parameter in my model has a value of 9, let us say this is a parameter, and I'm trying to estimate this parameter. Let me call it as some parameter mu. Okay. Now, I have some prior knowledge that this value should be roughly 9. Then if I were to use a frequentist approach, I'm not making use of any such knowledge. It is only the data is the only judge of what that value of mu is. But if you had some prior knowledge, then you could use a Bayesian approach in which you say that, for example, mu itself, you think of it as a random variable, and you say it has a tight distribution, okay, around 9. So the very likely value is 9. If you were not using data, it would tell you it is 9. But as you started using data, it would get pulled or pushed to one side or the other. So it is like a trade-off between your first principles knowledge and your data set. Now in this case, you have so because you're using new ways of describing that prior knowledge, all the parameters which go into describing these are known as hyperparameters. Okay, so we'll say, oh, because I needed to declare a density for this parameter mu, whose value was not completely known but it was close to 9, I would need to tell how wide is this density, and that becomes a hyperparameter. Okay, so a lot of modern approaches in AI ML try to actually optimize the hyperparameters themselves. Okay, so coming back to frequentist approach, it's purely data driven. So if you have n observations and A occurs NA times, then the probability of getting A is NA by n in the limit that n tends to infinity. But as I told you, you never have this luxury of n tending to infinity. You have only few data sets or few data points, and from that you have to make such judgment. So to give you an example, if let us say, if I have Mahendra Singh Dhoni, who has first 3 balls were dot balls, then or why take Mahendra Singh Dhoni? Let's talk about Hardik Pandya, who performed brilliantly in the T20s. So if he has scored 0 in the first 3 balls, then a frequentist approach would tell you, because there is no prior knowledge, would tell you that the probability of him scoring a 6 in the next ball is very low. In fact, it will be 0, because your data is just based, because your inference is just based on data. But if you knew that, no, I know that this person is a hard hitter, okay, and I could use some prior knowledge to come up with a Bayesian approach. And so in a Bayesian approach, I say, no, although the data is showing this, my prior knowledge tells me that the batsman is a hard hitter. Okay, and so I can slightly tune it towards whatever the prior knowledge is. Okay, and so this the way to implement it is through Bayes rule, and which we all have seen very often. So those are the two fundamental ways of looking at probability. And so whenever we talk about likelihood, we're talking about a frequentist approach. But when we are talking about a use of prior knowledge, we are talking about a Bayesian approach. Okay, so again, very quickly, just go through some terminology. In probability, we have experiment, and in the experiment, for example, if you're tossing two coins, then there are what we call as elementary outcomes. So if you're tossing two coins, then you have four possible elementary outcomes. Then you have a sample space, which is the space of all possible elementary outcomes. The null space, or the null event, sorry, which is which is an impossible event. Then you have events of interest, and this is something that which took me some time to understand, that I used to always think that outcomes is what is of interest. So it turns out that outcome is not of interest. What is of interest is what you as a designer would like to look at. Okay, and in this case, for example, if I say one head, then I know that my events of interest are head head, head tail, or tail head. So that is my event of interest. And why is this interesting, or why is this important? It is because if you can describe your event of interest carefully, okay, then your resulting probability problem becomes easier to solve. And if you do not describe it carefully, then you can see that if you were tossing 10 coins or 5 coins, it would just become, your events of interest would become too many. And so the counting would become that much more difficult. Then you have a complement of an event, E1, which is in this case would be just tail tail. You have set of all events. And here, if you see, we have the sample space in it, the null space in it, and all the events. Okay, so all the events means if I take any two events from this set and I take their union, it should also belong to that set. So if I take E1 and E2 over here, I will see that the union of E1 and E2 is nothing but a sample space. The intersection of E1 and E2 is nothing but the null set. If I take the intersection of omega and phi, or the null set, then I have again the null set. If I take the union, I get omega. So this set is a very important set. So if you we very often refer to it as the sigma algebra. So it is the same thing as what is in linear algebra. We first describe a field, and then on the field we describe a vector space. So in the same way, the set of all events is a sigma algebra, and under certain conditions it becomes a Borel field. So let's continue with terminology. So now I'm going to move to a random variable. So this is another step that we all have to overcome. And after we overcome this step, we often forget where we had come from. So if you see in this example shown over here, see, I as a designer, I am not interested. I am interested in some event. Did my reaction, is this a runaway reaction or not a runaway reaction? Okay, is the process safe or it is unsafe? Is my yield high or is it low? So I have this language in my head, and when I talk to a manager or to a business manager, we can talk in terms of this language. Okay, but this language, to be able to treat it, I need to convert it to some numerical value, and that comes through a random variable. So now you will see that you have you have an outcome I put here as an omega, and that outcome, so the omega belongs to the sample space. Okay, it had all the omegas in it, and from here you map it to the real line, and that is a random variable. So a random variable, like a lot of books will tell you, is not a variable, it is a mapping from that language that I understand. The yield is high, yield is low, to some number like 10, 20, 30. Okay, and that mapping is captured by a random variable, as I have said, omega. So why do we do this? We do this so that we can start using computers, we can start doing calculations, and it gives us an ability to quantify. And like we were talking about fuzzy in the previous lecture. So there is some, so expert systems, as we call them very often, are more qualitative, okay, and AI systems or ML systems tend to be more quantitative. So in this case, the moment I can put an outcome onto my number line, I have been able to quantify it. And if I quantify it, I would like to, so as a designer, I am not interested in, I am interested in the probability of my events of interest. I want to know what is the probability of E1. Whether you want to call that E1 as 100 or 200 on the real line, it is of no interest to me. Okay. But as I told you, that to talk about or do this probability counting is a difficult problem because we are dealing in a language space. So in order to go to a numerical space or a number line space, we do this random variable mapping, okay? And then I can capture, for example, I might be able to capture S3 and S4, which is my outcomes or my events of interest, by capturing the corresponding numbers on the real line. So this is a random variable, and then I can start talking about probability of E1 by talking about the probability of all events omega such that omega belongs to such that x of omega, okay, belongs to some set, okay, some A to B. So you see I've made a jump now. I'm still talking about probability of my events of interest, but now I am not talking in language space. I have done this random variable mapping, and I'm saying, no, tell me on that number line, what are the numbers that are of your interest? So it's like translation. You speak one language, you translate it into some mathematical language, and instead of counting probability in our language, we count that probability in that mathematical language. And this is where the notion of a cumulative distribution function comes in. So what a cumulative distribution function, as said over here, fx of x, does is it counts the probability for you in the real line. So we will define now fx of small x as the probability of all events omega belonging to omega such that x of omega, okay, is less than equal to x. So in I wanted to close the door anyway. So if so this is where that x is. So what is x? X is the random variable, and the small x which you see inside is that limit. So it is telling you that give me, if this x was over here, then it will tell you give me probability of all events which are captured from minus infinity to this value small x. That is cumulative distribution function. It cumulates all events from minus infinity to this x. Okay. So this is how we can continue talking about probability, but now start talking about it mathematically. And this is what I think of it personally as a $1 million picture, which clarifies. So you can see that I have a sample space which I had called as omega, and these are my events. These are my elementary outcomes. These are my events A and B. I am interested in knowing what is the probability of some event A. Okay, and this is that number which I wanted. But I don't go in this way. I actually do a random variable mapping. And so I go from the sample space through that x of omega. Okay, I am able to pick up what are these numbers which will capture A for me. So what is A over here is what on this number line. It need not be a continuous set. It could be disjointed sets. Okay. And then I will say, oh, I now know this probability, this cumulative distribution function. So can I find out what is the probability of this set and this set? Okay, and we will see how to do. So again, you are interested, you continue to be interested in the probability of the event A, but you go through this other mathematical language. So X was that random variable, and there are two types of random variables that you encounter, a discrete random variable and a continuous random variable. We'll look at some examples of both. So you know, fx of omega becomes this key, or this cumulative distribution function becomes this key vehicle to capture the information of probability in terms of that random variable. Okay, so it's a very, very important you know, tool that we use to be able to ascribe probabilities. So as an example, you know that this is your sample space. If you roll a die and you have 6 possible outcomes, okay, you also know that the probability of each of those outcomes, P of omega, is 1 by 6. So if I draw this over here, I am going over here and talking about probabilities of certain outcomes, or more interestingly, probabilities of certain events. But we don't do this. Okay, we don't do this. We first define a random variable, and in this example we have taken a random variable of 10 times omega I. So we go from here to this real line, or this random variable space, and then we have this notion of a probability mass function, or I'm sorry, a cumulative probability distribution function, which says what is the probability of all events. So this is shown over here. So you know, you have only 6 possible outcomes, either it is a 1, 2, 3, 4, 5, 6, and for some funny reason we have decided to map it as 10 times what is the outcome of that roll of a die. So then in terms of the random variable space, you have a real line which is going from minus infinity to infinity, but I know that you have 10, 20, 30, 40, and so on, which correspond to your those elementary outcomes. So what we do now is we go from random variable space to this same probability space by using this definition. So this cumulative distribution function is a much more intuitive way of describing probability than a probability density function. Although we'll see later that we almost always use a probability density function because it is easier to compute. But from a probability intuition point of view, it is the cumulative distribution function that gives directly a meaning in terms of probability. So fx of x is the probability of all events omega such that 10 of omega I is less than equal to x. Okay, I would interpret it that way. So if I told you, for example, and I think it comes up subsequently, that let me take an example. So what is fx of 38? I know that this is, so we stop writing these events because we become so comfortable. We just say it's the probability of x, this dummy variable itself. But that is a dummy variable. It is really the true way of writing it should have been probability of all outcomes omega such that minus infinity is less than x of omega is less than equal to 38. Okay, but we stop writing this. We just say this value of small x is 38, so give me the probability that this small x ranges from minus infinity to 38. Okay, and you now know that this probability is we had seen this here, so it is this. So 38 is here. Okay, and you know that it will be essentially 1, 2, 3 because you have 10, 20, 30, and so you will get it as half. Okay, so but we count it now not by counting the events that are taking place, but by counting just the probability directly from that probability cumulative density function. Okay, all right, so you know that, for example, fx of 82 over here is going to be 1 because you have captured all events after 60, because x, the probability of all events such that this x lies between minus infinity and 82 means you have got 10 lies between that, 20 lies between that, 30 lies between that. So all events got covered, and so that therefore the probability is equal to the probability of the sample space, which is 1. Okay, so as I told you, the probability distribution function is very, very closely related to the notion of probability directly. That means you can think in terms of probability, but we end up using the probability mass function or the probability density function. So the mass function, we use the term when we deal with discrete random variables, and continuous random variables, we will use the term probability density function. Though, when you start looking at books by, on AI and ML, people stop making these kind of distinctions. It is understood from the context whether you're talking of a mass or a density. So now, in this particular case, if you see, the probability density function or the probability mass function is very often known as P of X, okay, or it is known as small f of X. So capital F of X is almost exclusively used for probability, cumulative probability distribution, and the density uses either f of X or P of X, okay. So what is this probability mass function? So the probability mass function is a function, in this case, very simply, while cumulative was accumulating it from minus infinity to that value A, the mass function just tells you what is the probability at that value x is equal to A. So if I were to say what is the, fx of 30, then you know that fx of 30 would be just this much. Okay, this is the event. And so you know that is 1 by 6. Okay. And so you can see that I could have written this as fx of 30 as equal to fx of 30 plus minus fx of 30 minus. Okay, not minus 1, just minus. Okay, just before 30. When you think in terms of limiting values. And that will turn out to be 1 by 6. So this is very similar to the fact, so this is a discrete random variable. It has only some, the probability is, and that becomes very clear when you look at a probability mass function, that the probability is distributed discretely on that real line. Okay, it is not a continuous distribution. So it's not a requirement. You could have probability densities which could be continuous, and then there could be a sharp uptick, like a discrete change, and then there could be some other thing. So this is partly continuous and partly discrete. Okay. So from a math point of view, no, it doesn't matter. You can deal with both of them in a single framework, where they say like it is a Lebesgue measurable functions, which is using measure theory. You can deal with it, both of them, in a single framework. Okay, let's look at a continuous random variable. Now, a continuous random variable is like we said. So the cumulative, it doesn't matter. Cumulative is same. It doesn't see a distinction because this is directly connected to probability. So I'll also start writing in short form and just say x is less than equal to x, which actually, I will remember that there were events such that the random variable mapping is less than or equal to x. Okay, but it's the same thing. It doesn't matter whether it is continuous or discrete because it is just in the directly connects to probability. But there is a difference when you look at a probability density function. So instead of a mass function, we call it a density function. And it is very simple. If you think of it in terms of why in engineering we use density. So you might have, for example, rho of x. So if let us say I have some pipe and it has some density rho of x, then I need not tell you what is the mass, because that will be like a cumulative distribution. I tell you what is the mass from here to here, then I tell you what is the mass from here to here, and so on. It is much more, it is very difficult to to deal with it. It is much simpler for me to find out the mass anywhere if you give me what is the density, the mass density distribution. Okay. And if you give me, I can very easily use this to find out the mass wherever I want. So if I wanted to find the mass between 2 points, A and B, I would just say, okay, this is A, this is B, and the mass between them is this, by just integrating the linear density. And the same thing is true over here. So I can use this density to be able to talk in terms of the probability. So we can say that the integral of that density from A to B is nothing but the probability of the events such that its random variable mapping in the real line lies between A and B. Okay, so it's a, you know, there's a direct connection between a density and a distribution. Okay, so given a density, you can always find a distribution. And how will you find it? You will say f of x is equal to the integral. You wanted the probability. This tells you, this is asking you for this probability, x being less than equal to x. So it starts from minus infinity, goes all the way to x, and this is your density, which is capturing that probability. Let me call it fx of x prime dx prime. Okay, so see, from your probability density, you could calculate your distribution. Okay, now if this is the probability, you will also realize that I could have used my density and written this as fx of b minus fx of a to be able to get the same probability. Because when you are from minus infinity, this is b, this is a, then you're saying probability of all these events minus probability of these events. This is disjoint. Okay, and so that gives you the probability from a to b. So the density turns out, so the density turns out to be a more useful tool in terms of calculation of probabilities. And you know, there are these what you can call as branded densities or named densities, which are very popular in all our work, in most of our work. And why we say that, for example, let me see. So an example is a uniform density, okay, or a uniform distribution. So note that, you know, how given data, like in that refinery example, and I have an error, and I'm trying to now quantify uncertainty in that error, I have to make some comment on what is its underlying density. So the simplest approach now is to make an assumption that that density belongs to some named or branded kind of a density, an example being uniform. These are known as parametric densities. Of course, you have non-parametric densities too, and that is another very big player in AI ML kind of literature, where you can actually do kernel estimation of densities or kernel density estimation, which is very similar to a k-nearest neighbor kind of an algorithm. Okay, so let's look at this this uniform distribution. So you will see that these names tend to connect not to the cumulative distribution, but you will see that this uniform makes much more sense when you use the underlying density. Okay, so what is a uniform distribution? A uniform distribution is that if I were to get a phone call between times A and B, okay, there is no chance that a phone call comes before. So what I'm drawing here now for you is fx of x. There's no chance that the phone call comes before A. Maybe I've turned it off, it won't ring. I've turned it on, and now there is an equal chance at any delta that I take, I see that there is an equal chance that I get a call. Okay, which means that if I look at f of x plus delta minus f of x of delta, this is basically the probability of getting a call between x plus delta and and x. Sorry, not and x. Okay, that is same, that is uniform. You take, it does not depend where you were between A and B. You take any point, go delta away, the probability of getting a call in that interval is same, doesn't matter where you are. That is a uniform distribution. And that, from this argument that I have made, you see that it's a constant slope line from A to B. Okay. And then after B, I turn off my phone. So there's no chance of getting a call. You know that this should be 1. Okay. Because all probability, all events get covered when you say X is less than equal to B. So it should be 1. Because X less than equal to B is another way of saying minus infinity is less than X is less than equal to B. Okay. So this is that equation. This is a straight line passing through the origin. Okay. So this is your cumulative. Now, if you were to write this as a density, then you can differentiate it. Just like you can differentiate mass with volume to get density, you can differentiate this in order to get the probability density function. And you will see that the word uniform makes simpler sense, at least to me. Okay, it makes simpler sense. If I put A and B, it is uniform. I say, okay, it is like the mass is same everywhere. Okay, and it tells me, it's uniform, it's straight. Uniform means same, not changing. Okay, so it's much simpler to be able to interpret things when you think in terms of density. And now it is clear that, we had seen that integral from let me write x to x plus delta x, the fx of x dx is nothing but the probability that it lies between x and x plus delta x. And this height, by the way, is 1 over b minus a. So I know that as long as I take any infinitesimal element delta x, the area of that rectangle, which is what the probability gives you, is the same. Is b minus a times delta x, or 1 by b minus a times delta x. Okay. All right. Let me see how am I doing on the time? Oh, it's 9 o'clock, so I have half an hour more. So I've been, so Professor Mani will look at this again. So whatever I miss out, he can carry on from there. But as I thought, I will not make it very fast or something, just at a leisure pace in the beginning. So we have now seen what a probability mass function is, what a probability density function is. The next topic is, the thing is, the probability density function gives you cannot ask for any more information than the probability density function. Because as I said in the beginning, that the probability density function gives you the stable behavior of those realizations which you see in one measurement. So you see some realization. It is like this. Now, when you toss a coin once, you don't know whether it will be head or tail. But the density tells you what is the stable behavior of that coin. Okay. So it is, you cannot ask for anything more than that. It is like complete. It is like the first principles information or complete information of that random variable, okay, or the random setting. So it is too much of an information, and what we typically are much happier with are a few moments of that random variable. So for example, Professor Goody was talking about coherence and he was talking about higher order statistics. So in the same way, instead of asking for the full random variable, for the full density or equivalently the cumulative distribution, we just ask for some moments and we say we'll be happy with that. And it's very interesting that, by knowledge of a few moments is very often enough to completely characterize an underlying density. So you know that the underlying density of my error could be uniform, okay, or it could be Gaussian, or it could be exponential, and so on. And I was just playing around. Let me show you. I'd gone to Octave just to see how I could this thing. So what I realized is that this. I hope you can see my screen. So you can see that there are so many different types of distributions which are there. So you have, and every distribution has a very interesting story to tell. So particularly when you're teaching to undergrad, or as a first course, it's very nice to get a story. So for example, if you're talking about binomial, you know that you can talk about a Bernoulli trial where you have a binary outcome, yes or no, and then you want to have what is the chance of getting 4 yeses out of 10. That is a binomial. Okay. If so, I can also see Poisson over here. So for example, Poisson is a discrete random variable. So
Sir, we cannot see the histogram.
but can you see my screen?
I can see your slide, moments of random variables.
Oh, oh, it is because I'm sharing my PowerPoint and I'm not sharing my screen. So let's just try to see if I can share my screen. I have stopped sharing now, and let me go to share, and there is a screen. So maybe I'll just share the screen. Yeah, you should be able to see now.
Yes, yeah.
Yeah. So I've opened Octave, which is, so, this is this challenge as a teacher, that we often end up using tools which is often, is a paid version or something, and then you teach a student and then the student goes out, they don't have access to it. So if you are teaching, it turns out that a lot of things that we do in MATLAB, you can do in Octave. In fact, I have originally written my codes in MATLAB, but I see that mostly without any changes, they work in Octave. And this is true about this. So I have first time I saw that this same command is there also in Octave. So I was trying to talk to you about these distributions, and the command I was using was PDF. So PDF is a command, so you can ask it to give you the value of that PDF function. But there are so many branded densities that you have here, more than 15. So I was talking to you about a binomial. So that I had shown was this. So you know that it has 2 parameters. So it's a 2-parameter family of densities. You need to know number of trials. So these are Bernoulli trials. Answer is yes or no. And what is the probability of success of a particular trial? So it's 2 arguments. Okay. I was going to Poisson, and I was saying, if you see this Poisson over here, it's a discrete random variable. Binomial is a discrete random variable because you're talking of the probability of number of successes. In Poisson is when you're using, for example, queuing theory, or the number of logins in a given amount of time. So number of something in a given amount of something is a Poisson distribution, but it's number, and so it's a discrete random variable. Number of, most commonly in books you will see number of misprints on a page is a Poisson distribution. Number of people who come to a post office in an hour's time is a Poisson distribution, and very popularly used because it can be highly, analytically used to obtain various expressions, and that's a Poisson distribution. And so if you say now, okay, number of misprints in a or number of defects in a wire is a of 1 meter is a Poisson distribution, then the length to the first defect or the length to the next defect is an exponential distribution. And you can see that that is also over here. So, they have very nice stories related to each of them. And, you can discuss this very nicely in the class. You have the normal distribution. And so I was trying to see that, how could I plot it? And I realized that it's very simple. For example, I use this y is equal to norm PDF, and then I just plot the x values I have given, and I have told it, so the norm PDF, the first value is mu and the second value is sigma. A normal distribution, it requires only 2 parameters, the first moment and the second moment, mean and the variance. And you can see that, you can very nicely plot it. And that is what I was, I was playing around after our, so you see, you can get this. You can plot, a whole lot of different types of distributions. So these are those different distributions that we have been talking about over here. And now that we have spoken about these distributions in an abstract sense, where we said it is f of x, okay, we know that there are a lot of these branded distributions, which we saw, like for example, uniform, Poisson, and so on. Okay. Now, as I was saying, that it is very often sufficient to not talk about that entire density, is too much of information, but just be content with moments. For example, in a normal distribution, it turns out that if you give me mu, the mean, and the variance, you actually, and you tell me that the underlying distribution is normal. Okay, you have to make that assumption. Then I know the full density. So moments are very often enough to describe density. Okay. So the mean of exponential distribution e to the power minus lambda x is lambda. So you know the density itself uses a moment often directly, not always. We saw in a uniform distribution it is not necessarily the case, but very often knowing the moments and making the assumption of what is the underlying density gives you full information about that particular density. All right. So now let's go to these moments. Okay. So there is this notion of an expectation operator. And just like, you know, a Laplace operator or many other operators, once you get a hang of it, is very simple to use and it can allow you to solve significant problems. So one of these is known as, this is this expectation operator, which is used in order to find what is the different moments. So the simplest moment that we find is just the expectation of x. And so this indeed is the definition of the expectation operator. If you have a continuous random variable, and this is the definition if you have a discrete random variable. Okay, it is just the mean of those values. And you know, for those of you who use who work in quadratic theories in different kinds, you will realize that this mean is actually the solution whenever you're trying to minimize an L2 norm, mean square. Okay, so when you're trying to minimize the mean square error, the solution is some kind of a mean. Okay, and so it has a lot of significance, just this mean, in a lot of theories, in mathematics or in control theory, in data science, and so on. So so with this, let's go forward. So you will realize that this is nothing but like a center of gravity that you can, you know, the mean is the center of gravity of the density function. So it has the same, it gives you the measure of central tendency. So the mean, which we mostly call as mu. So if you realize, when I'm writing mu as integral from minus infinity to infinity, x fx of x dx, I am talking about the population mean. So I, you know, confess that when I was, you know, it took me a long time to understand this difference between a population and a sample. That the population is because I'm talking in terms of a density. It is that entire ensemble, which I never know. And so this is really the population mean. And that sample mean is usually like this 1 by n summation of xi. Okay, those few samples that we see. And this we often called as x bar. And this we use to be able to give some statement on mu. You're never interested in x bar itself. Although you did your experiment, you got that, but you know that if you were to do that same experiment again, you would not get your x bar back. But you're not interested in x bar, you're really interested in mu, the population mean. So what we are talking about here is indeed that population mean. Okay, so let us say you have a uniform random variable. Okay, how do I know it is uniform? Because if I draw this, another thing that I like to do is draw, you know, it for people who are not very algebraically inclined, it clarifies a lot of things very easily. So this is your uniform. Yeah, it is 1.5. It is constant over that entire range. And so I see that, you know, it is a uniform distribution. The question is, what is the expected value of x? You know that the definition given to you was integral x fx of x dx from minus infinity to infinity. And so you can easily solve this. You know that the integral will pick up area only between 0 and 1.5. And so it is x times 1 over 1.5 dx. And if you solve it, you will get your answer of 0.75. So it is very comforting to know that 0.75 lies right in between 0.75. So it gives you that measure of central tendency. Okay. So if you were to use, you were trying to minimize x minus mu the whole square. Let's say these were some samples. Then this, and you have taken all possible samples. Then this mean so this you are trying to minimize with respect to mu gives you that mean square error solution, least mean square error. Okay, it connects to that least mean square. Okay, so very often it turns out that you have, and this turns out in almost any problem of interest, any problem of engineering interest. So our friends, who do Monte Carlo simulations and so on and so forth, they assume randomness in X. But this X is used to calculate some Y. So let's say Y is equal to G of X. So G is a deterministic function. The function itself is not random. If I say Y is equal to sine of X, you give me X, I'm going to give you a deterministic value of Y. But because X is random, it turns out that Y is also random. If X had a density fx of X, then the immediate question is, how does this density propagate into Y? Or how does this uncertainty in X, which was quantified using this density function, propagate into Y? And so ideally, I would like to find out what is f of Y. Okay. So it turns out that this is not always an easy problem. To go from this density fx of X to the density of the induced random variable fy is not an easy problem. Very often it's quite difficult. You can try to do it numerically, and this is what a lot of ensemble driven methods, like for example Monte Carlo, or if you do state estimation, then we do all kinds of Monte Carlo kind of filters, state estimation filters. Or like in biology, you have some gene which is binding and unbinding, okay, and you make assumption of some uncertainty over here. So you have some binding and unbinding, but the gene does a lot of things. It goes into an mRNA. From mRNA you go into a protein. From protein you go to some action, some catalysis or something. So you want to know what is the effect of uncertainty over here on my action. So you see, this is g of x. It goes through a lot of transformations. So knowing the density over here does not mean that you know the density of your y. So that is a very distinct, is a very difficult problem. You can try to solve it, okay? But it turns out that the expectation is very simple to solve. Instead of the density, the expectation is a much simpler problem to solve. So, and so it turns out that it is very easy to solve for the expectation. That is, to find the expected value of y, I don't need to know the density of y. I can find this expectation only through the density of x by just doing this. And since very often we are only interested in mean, this is the step which is almost always followed, that okay, I don't, as I gave you that example of an mRNA going into a protein, I can at least tell you what is the mean action of that protein, given that there is some uncertainty, or I can tell you the spread, the variance of that action. Okay, so that brings us to variance. Again, you can think of it in terms of an expectation operator, and if you were to expand this, you would see that this is x square, and expectation is a linear operator. So then I can write this as minus 2 mu into expectation of x plus expectation of mu square. mu is a constant. So expectation of a constant is a constant, because if you were to do that and write down mu square fx of x dx from minus infinity to infinity, this mu square comes out and the integral moves over here, and this integral is simply 1. So this is just 1. So you get plus mu square minus 2 mu into expected value of x, which is mu. So you finally get this expected value of x square minus mu square. And this is a very popular thing. So if you are doing a course on AI ML, you see this very often, what they call it a bias variance trade-off. So you know that this mean square over here is a sum of the mean, square of the mean and the variance. So if you think in terms of error, then we say mean square error is equal to bias square plus variance. Okay, and this is where it comes from. But it is simply, you know, how to calculate it using an expectation operator. So I know how to use this. Whatever is inside, I make it as the integrand. So I make it as x minus mu, the whole square. Then I multiply it by my density. And that becomes, and from my over the entire real line on which that random variable is defined. So that becomes my variance. Okay. So if you were to find, so you know, just the first, so if you think about it, this is known as the second central moment. Why is it a central moment? Because you have centered it. If you take data x and you subtract the mean mu, this I call it as xc, the centered data. In almost anything that you do in machine learning, the first step we do is we take the data, find the sample mean and subtract it out. So we call it mean centering. So this is centered data, and that is why this expectation is a second moment, because there is 2 over here and it is a second central moment. So you can now, you know, talk about any moment. So this is the non-central moment, like the mean, expected value of mean is the first non-central moment. And this is the nth moment. And how to find it? We know that you do x to the power of n fx of xn dx. Oh, there's no n here, from minus infinity to infinity. So this is that expectation. It turns out, you know, that you don't need to very often use expectations in terms of this integral, but just expand it like how I showed you for that mean square error case. Okay. So let me continue now. I have already shown you these different probability densities. What we have now know is the next step, and the next step is calculation of when you have two random variables. So when you have two random variables, x and y, because you know a single random variable is only of book interest. If you are solving a real problem, you will always have multivariate regression. Okay, everything is multivariable. It's complex. You cannot just solve it as a single variable. And so we talk in terms of multiple random variables. Now, for those of us who know of vectors, this becomes very straightforward. Is it? You can hear me through the computer? Okay. At what point did I get disconnected? Can you tell me? Okay, okay, great, great. You called me. That was just in time. Thanks. So, yeah, I hope everybody can hear me. So I was trying to tell that um, that you know, we can talk in terms of two random variables and nothing really changes because I'm still talking in terms of that event or outcome of my experiment, and that outcome is omega. But now my outcome is all all those cases where the probability of a height, or I'm sorry, all those cases where the height is less than 5 feet and the weight is less than 55 kgs. Okay. So in all these cases, you have the case where that is my outcome or of interest. Okay. So I can now start talking about probability of those. And you will see that what has happened is earlier I had only one x of omega being less than or equal to x, and now I have two. So I have this as fxy. So this is a bivariate distribution. And in this case, we talk in terms of joint probabilities. Okay. So I know I've also run out of time. So I will probably just, you know, talk to you about this density and stop. So this is the last slide that I'm going to talk to you about. So now we have the case of a joint probability. So now you have x, you have y, okay, and you have this f of x comma y. So it becomes a 3D plot. Although there are only two variables, it becomes a 3D plot. And you have the same kind of a connection between density and the distribution as before. So before we had the following for 1D, and now you can see the connection between 1D and 2D. So fx of x is equal to the integral from minus infinity to x fx of x prime dx prime. And in this case, you have now two integrals because now the probability connects to a particular plane. So you need a 2D, and this, the probability of this plane will be connected to um, to this cumulative distribution function. Okay. So again, all the things that we discussed before would carry forward. So let me stop here. There have been some difficulties with the video. So let me stop sharing. Yeah. So I will stop sharing. If are there any questions that you would like to uh, discuss? I hope you can hear me. Can somebody just confirm that they can hear me?
Yes, sir, I can hear you, sir.
Okay. Yeah. So you know, we just went through some very basics of probability theory. As I told you, we discussed and then we decided let's do it because a lot of things that Professor Manibhushan will talk to you about, confidence intervals, connects directly to the probabilities. So are there any questions you would like to ask? I'll be happy to answer.
Sir, I have one query.
Yeah.
Is the
Yes,
mean
Swapna.
calculated over the normalized data or only the whatever the raw data we take it?
Is the mean translated?
Mean calculated for normalized data using the normalized data or normally taking the overall data we take?
So you calculate the mean based on raw data. So that tells you the central tendency of that raw data. But whenever you are using data for, let us say, for PCA,
Okay.
the first step we do is we center it. So you don't need to. So typically, it depends what you want to do with it. If you're using, for example, an ANN or linear or
ANN.
some kind of regression, you
Yeah, for
will typically,
ANN.
yeah. So for ANN, it is very often that we actually scale the data. So it is known as preconditioning of the data or pre-processing of the data.
Okay.
So very often people use a PCA for the ANN, take the dominant principal components and use them as an input. So when you're doing that, you have already normalized the data, because you'll see in PCA, the first step in PCA is to find the covariance.
Okay.
And how do you find covariance? By first you center it.
Yes.
So very often the centering becomes a part of that algorithm itself.
Okay. Thank you, sir.
Sure. Any other question? Okay, so if not, we can conclude our presentation for today. Again, apologies for all these hiccups that happened, you know, uh, and that is that erratic and uncertain part that we have to factor in any good design. So good night, everybody, and Professor Mani Bhushan will take over tomorrow. Okay, then. Bye. You can disconnect from the meeting. Thank you. Om Prakash, I should stop the recording, no?
Yes, sir. Yeah, stop the recording.